Hello everyone. Today our topic is a continuation of virtual structures, that is nothing but virtualization of CPU and memory and IO devices. Today we are discussing the topic what is virtualization of CPU, and later we have to discuss memory virtualization and one more the concept input or output virtualization. And coming to the concept of virtualization of CPU, it is nothing but a virtual machine is a duplicate of an existing computer system in which a majority of the virtual machine instructions are executed on the host processor in native mode. Thus, unprivileged instructions of virtual machines run directly on the host machine for higher efficiency. And coming to the other critical instructions should be handled carefully for correctness and stability. What it means in the sense, we have to support virtualization and processors such as the program files x86. It employs a special running mode, and instructions is nothing but, we want to say, the known as, it's nothing but hardware assisted virtualization. In this way, we have to learn virtual machine monitor and guest operating system run in different modes and all sensitive instructions of guest operating system and its applications, or it is tapped in virtual machine monitor for the program files architecture x86 and Intel, and what the proprietary technologies for hardware assisted virtualization. And coming to the next point, we have seen the critical instructions are divided into three categories. How many categories? The critical instructions are divided into three categories, namely privileged instructions, and the second one is control sensitive instructions, and the third one is behavior sensitive instructions. Okay, now coming to the what does it mean in coming to the concept of hardware support for virtualization concept, we have to learn some modern operating systems and processors. It is permitted to multiple processors to run simultaneously. If there is no protection mechanism in a processor and all instructions from different processors, it will access the hardware directly and may cause a system crash. Okay, and coming to the all processors have at least two modes. For coming to the first mode is nothing but user mode, and next one is supervisor mode, in the sense to make sure that to ensure controlled access of critical hardware. We have to control accessing of critical hardware. And coming to the concept of instructions is these are running in supervisor mode, or nothing but, we have to say, that is nothing but privileged instructions. Okay, what is the privileged instructions? The instructions running in supervisor mode are called as privileged instructions. Okay, it execute in a privilege mode and it will be trapped if it is executed outside this mode. And coming to the concept of control sensitive instructions, it's nothing it attempt to change the configuration of the resources what we are using. Okay, in the sense, other instructions or unprivileged instructions in a virtualized environment. Okay, it is more difficult to make the operating systems and applications to run correctly. Okay, because there are more layers in the mission stack. Okay, we have seen for example, in the CPU we have seen the Intel hardware support for virtualization of processors and memory and IO devices. Okay, we have to learn if for our CPU concept. Okay, coming to the control sensitive instructions is nothing but we have to attempt to change the configuration of resources whatever we have to use. Coming to the behavior sensitive instructions, in the sense instructions is nothing but something statements. Okay, what the behavior sends to instructions, it have some different behaviors. Okay, depending on the configuration of resources, including the memory, including the virtualization of processors, memory and IO devices. Okay, coming to the concept of coming to the concept, this is a continuation or a CPU architecture and virtualization of CPU. Here, coming to the CPU architecture, it is virtualizable if it is supports the ability to run the virtualization missions privileged. Okay, what it does says means in this a CPU architecture, it should be virtualized and it will be supported to ability to run the virtualized missions. It's as privileged. And coming to the unprivileged instructions in the CPU, coming to the user mode, while the virtual mission monitor runs in supervisor mode, when the privileged instructions including the control and as well as behavior sensitive instructions of a virtual mission are executed. At that time they are trapped in the virtual mission monitor. In this cases, during the virtual mission monitor, it acts as a unified mediator for hardware access from different virtual missions to guarantee the correctness and stability of the whole system. However, we want to say not all CPU architectures are virtualizable. Okay, coming to the RISC CPU architectures, it can be naturally virtualized because all control and behavior sensitive instructions are nothing but privileged instructions. On the context, what we say in the sense, the program files x86, its a CPU architectures are not primarily designed to support virtualization concept. Okay, nothing here ma. What does it means in the sense, when the privileged instructions, we have to include the both instructions like control and behavior sensitive instructions of a virtual missions, these are executed. When they are executed, they are trapped in the virtual mission monitor. So in this case, the virtual mission monitor acts as a unified mediator for hardware accessing, okay, support from different virtual missions. What the guarantee the correctness, the stability of the whole system to run or processor memory and IO devices. However, not all the CPU architectures are virtualizable. Coming to the in RISC CPU architectures, it can be virtualized, naturally virtualized, because the all control and behavior sensitive instructions or privileged instructions. And coming to the context, the program files x86 in a system, the CPU architectures are not primarily designed to support the virtualization concept. And coming to the concept of memory virtualization, you know, memory, in the memory you have to store some data in the memory. It's a virtual memory we have to use. It's nothing but virtualization. It's a similar to the virtual memory support. Okay, it is provided by the modern operating systems. Okay, in a traditional execution environment, the operating system maintains mappings of virtual memory to mission memory by using the page tables, which is a one stage mapping from virtual memory to mission memory. Okay, what does is nothing but we have seen the virtual memory is nothing but we have to say some virtualization. It's a concept is similar to the virtual memory. It's supported to provide by modern operating systems. In traditional way, we have to see in the execution environment. In that operating system, we want to maintain the mappings of virtual memory to the mission memory by using the tables called page tables, which is one stage we have to mapping from the virtual memory to mission memory. In the sense, the all modern program files of CPUs include a memory management unit is nothing but MMU, and a translation it look aside buffer in the sense TLB, in the sense translation look aside buffer, to optimize the virtual memory performance. Okay, we want to say, however, in a virtual execution environment, the virtual memory virtualization, it involves the sharing of the physical system memory in random access memory, and it is dynamically allocated to the physical memory of the virtual machines. Whatever we say, in the sense, in a virtual execution environment, VEE, in that concept, the virtual memory virtualization, it involves we want to sharing the physical system memory in random access memory, and we want to dynamically allocate the physical memory to the virtual machines. That means a two-stage mapping processes should be maintained by the guest operating system and the virtual machine monitor respectively. Okay, the nothing but virtual memory to physical memory, and one more physical memory to machine memory. In that concept, what we want to say, in the sense, if you have to learn a memory management unit virtualization, it should be supported, which is transparent to the guest operating system. Like the guest operating system continues to control the mapping of virtual addresses to the physical memory addresses of virtual machines. Okay, but the guest operating system cannot access directly the actual machine memory. Okay, coming, and we want to say the virtual machine monitor, it is responsible for mapping the guest physical memory to the actual physical memory. Okay, this is the concept of memory virtualization. And coming to the, we have to learn here IO virtualization. What is IO virtualization? We have to learn in detail now. There are three ways to implement IO virtualization, that is nothing but full device emulation and para virtualization and direct IO. Okay, in the sense, what is the meaning of IO virtualization? What does exactly it means? In the sense, what it did, in IO virtualization, it involves we want to managing the routing of IO request between virtual devices and shared physical hardware. At the time of this, we want to writing, there are three ways to implement the IO virtualizations. First one is full device emulation, and next one is para virtualization, and the next one is direct IO. Okay, coming to the concept of what we want to say, the full device emulation is the first approach for IO virtualization. Generally, this approach says, what do you says in the sense, what says in the sense, it emulates well known and real world devices. Okay, what generally this approach emulates well known and real world devices, all the functions of a devices or bus infrastructure, such as device enumerations and identification and interrupts and direct memory access, are replicated in that software. Okay, it's nothing but what we want to say, full device emulation. This software, it's located in the virtual machine monitor, and it acts as a virtual device. The input, the IO access requests of the guest operating system are trapped in the virtual machine monitor, which is interacts with the interacts with the IO devices. Okay, this is nothing but full device emulation approach. In the sense, the IO virtualization accessing request of the guest operating system, or it is trapped in the virtual machine monitor, which interacts with the IO devices. This is the concept of full device emulation. And coming to, we see the para virtualization. In that full device virtualization, a single hardware device, it can be shared by multiple, in the sense of more than one virtual machines that can run concurrently. However, we want to say the software emulations, it runs much slower than the hardware it emulates. Okay, and coming to the concept of para virtualization, what does it means? In the sense, we want to say the para virtualization method of IO virtualization, it is typically used in Zen architecture. It is typically used in Zen. Okay, it is also known as, we have to say, split driver model. What driver model it want to say? One more name we have, split driver model. It consisting of a front end driver and a back end driver. Okay, it consists, what it consists, front end and back end drivers it consists. Okay, it achieves, what it achieves here, it achieves first of all, we have to learn the front end driver. What it done, in the sense, the front end driver is running in domain U and the back end driver is running in domain O. In previous classes we explained the Zen architecture, domain O, domain U. In that, the front end driver is running in domain U and the back end driver is running in domain O. They interact with each other via a block of shared memory. Okay, a block of shared memory, they can interact. And coming to the front end driver manager, the IO requests of the guest operating systems. Okay, front end driver manages the IO request of the guest operating systems. And coming to the back end driver, it is responsible for managing the real IO devices and multiplexing the IO data of different virtual missions. Okay, although we want to say the para IO virtualization, it achieves the better device performance than full device emulation. It comes, okay, then it comes with a higher CPU overhead. And coming to the direct IO virtualization, what it says, in the sense, let us take, we want to take the virtual mission access devices directly. Direct IO virtualization, let's the concept of direct IO virtualization, virtual mission access devices directly. It can achieve close to native performance. What it achieve? The close to native performance without high CPU cost. What now we want to say? Without high CPU cost. And coming to this current direct IO virtualization implementations, what it focus, in the sense, the implementations, we want to focus on networking for mainframes. What ma? Networking for mainframes. There are a lot of changes for commodity hardware devices. They have some changes, in the sense, there have so many lot of challenges for commodity hardware devices. For example, when a physical device is reclaimed, in the sense, required by workload migration for later reassignment, it may have been set to an arbitrary state. For example, direct memory access to some arbitrary memory locations that can function incorrectly or even crash the whole system. Okay, what we want to say, the current direct IO virtualization, it implements the what that focus on, in the sense, networking for mainframes. There are a lot of challenges for commodity hardware devices. For example, we want to suppose when a physical device is reclaimed, in the sense, required by workload migration for later reassignment, it may have been set to an arbitrary state. For example, direct memory access to some arbitrary memory locations that can function incorrectly or even crash the whole system. Okay, and coming to the one more concept, software based IO virtualization, in the sense it requires a very high mm, overhead of device emulation. And coming to the hardware assisted IO virtualization, it is so critical to do the task. Okay, what we want to say, software based IO virtualization, it requires a very high speed of device emulation. And coming to the hardware, it assisted the IO virtualization, it is critical. Okay, this is the concept of IO virtualization. Later, we discuss the concept of virtualization, virtual clusters, and resource management. What the topic? The next topic it should be virtual clusters and resource management. Okay, later we discuss in further video. Thank you.